So here are some news articles about quantum computing from the last year. Quantum computers may be more of an imminent threat than AI. How quantum computing can rock the world of Bitcoin mining. Stealing Bitcoin with math. Quantum computing is advancing so fast that Bitcoin could become hackable in months, not years. And this is an article from October of last year, so some months have passed, but we still haven't seen this come to fruition. So quantum computing is a topic about which there's a lot of hype. It's also a topic that's difficult to explain in a popular news article. It's a topic that's difficult to explain in 15 minutes. But that's what I'm going to try to do a little bit today, and to dispel some of the common myths that you see about quantum computing in the media. In particular, me and some colleagues saw articles like these talking about the impact of quantum computing on Bitcoin, and we wondered how realistic they were. So we actually set out to do a more scientific analysis of the impact that quantum computing might have on Bitcoin. And I'll share some of those results with you today. So first, I need to tell you a little bit about what quantum computing is. And we're going to start by going back to what classical computing is, something more familiar. So classical computers, they operate on bits, right? What's a bit? It's just a 0 or a 1. Now, ultimately, this information on a computer has to be stored in a physical way. After all, a computer is a physical device. So for example, here in a hard drive, usually information is stored in terms of magnetic charge. A magnetic charge can be positive or negative, and we can use this to represent our 0 and our 1, our bits. Now, quantum computers operate on something called qubits. This just stands for quantum bits. So quantum computers still store information in terms of zeros and ones, but quantum computers store this 0 or 1 in some of the tiniest particles of matter. For example, an electron, or a particle of light, a photon. So for example, an electron has a property called spin. And this spin can be either up or down. And now we can use the spin of an electron to represent our 0 and our 1. Now, because an electron is such a tiny particle, it doesn't follow the laws of classical physics that we're familiar with in the macroscopic world. It follows the laws of quantum mechanics. And one thing that quantum mechanics says is that an electron can actually be in what's called a superposition of these two states of being spin up and spin down. It means that it can kind of be both spin up and spin down at the same time. Now, of course, this is quite an unfamiliar concept to us. So I want to kind of try to illustrate this with a little bit of an analogy. So let's say that we have a die. So I don't have a large die, so I'm using a Rubik's Cube here. And let's say that I mix up this Rubik's Cube, okay? And then I cover it up with a cloth, okay? Now let me mix it up some more. So now one side of this die is facing up, right? But we don't know which one. So how can we describe the state of the die? So I think that we can describe it in a probabilistic way, right? That would be one way that we could describe it. And if you believe me that I mixed it up really well, then we could say that with probability 1/6, the red side is facing up. With probability 1/6, the yellow side is facing up, etc. Okay? So that's similar to what a superposition is. When an electron is in a superposition of being spin up and spin down, it means that when we measure the electron, when we actually look at it, we have some probability of seeing it being spin up, some probability of seeing it being spin down. Okay, the same thing as when I measure this, we see that a definite side is up. Okay? Now, one difference between the electron and the die is that when this die is underneath the cloth here, I'm sure that all of you believe that there is a definite side facing up. And it's not my measurement that causes one side to be facing up. Now, quantum mechanics is a little bit different. When the electron is in a superposition of being spin up or spin down, the outcome isn't determined. Somehow this outcome is determined by our act of measuring. One other important difference between the electron and the die is that an electron it has what we call amplitudes. So we can have some amplitude on the spin-up state, some amplitude on the spin-down state. When we actually measure this electron and look at it, the probability that we see the electron being spin up is equal to the amplitude squared of the spin-up state. So these amplitude squareds behave like probabilities. But the amplitude itself can be a positive or a negative number. And that's an important difference between quantum mechanics and probability distributions. The fact that these probabilities can be positive and these amplitudes can be positive and negative means that we can have interference. So it's like when you have two water waves coming together, when you have the crest of a wave hit a trough of a wave, they can cancel out. And that's really the game that we play in quantum computing. We try to cancel out amplitudes on solutions that are not correct, and we try to amplify the amplitudes on good solutions, so that when we measure this state, we have a high probability of seeing the good solutions. So that's kind of the one-slide summary of what quantum computing is, and the game that we play as quantum algorithm designers. Okay, now let's talk a little bit about where the state of the art in terms of quantum computing is right now. So Google and IBM have already built quantum computers that have 50 qubits. So qubits is kind of the number of qubits is one metric that we have for measuring the development of quantum computers. This is kind of a necessary but not a sufficient condition to performing quantum algorithms. You can think about the number of qubits as something like the amount of RAM you have in your computer. So it's about the amount of memory that we have to act on. And of course, we need to have a fair amount of memory in order to run interesting algorithms. So right now we're about the 50 qubit level. In the past couple years, we've seen a lot of increasing interest on the commercial side of developing quantum computing. So now there's many startup companies that are developing quantum computers. Of course, it's an active research area in universities. And we're seeing these large tech companies really getting involved, like Google, IBM, the big Chinese tech companies, Alibaba, Baidu, Tencent. They're all getting involved in developing quantum computers. So here we have a little projection. So taking some of the number of qubits that we've already seen in quantum computing devices. And we see something like a Moore's law. So the number of qubits has been doubling every 8 to 12 months. So here you see a projection of what that would be if the doubling continues every 8 months or every 12 months. And probably to start doing interesting algorithms, we're going to need to have in the area of hundreds of thousands of qubits. Okay, so we're looking at probably still another 10 years out before we get something like 100,000 qubits. Okay, so finally, let's say that we build these quantum computers. What are we going to be able to do with them? So first of all, let me dispel a popular myth that you see in the media, and that's that quantum computers are just an extremely fast version of our current computers. Okay, so that's not true. In fact, quantum computers are not going to be better at solving every problem. Quantum computers really process information in a different way. As I said before, they try to exploit this positive and negative interference in order to find good solutions. So that means that problems really have to have a certain kind of structure in order for a quantum computer to take advantage of that structure and lead to a faster algorithm. Okay? So far we've seen two really killer applications that a future quantum computer can have. And these were actually developed in the mid-1990s, in the very early days of the study of quantum computing. So the first application is to breaking cryptography. This is something called Shor's algorithm that can be used to factor large numbers. So to factor a number means to write an integer as a product of prime numbers. Okay, so you might ask, why is that interesting? Well, RSA is a very popular crypto system. For example, it's used as part of the HTTPS protocol that secures traffic over the internet. And the security of RSA is actually based on the hardness of this problem of factorization. Okay, so the fact that a quantum computer can actually do this factorization quickly means that RSA is completely vulnerable in the presence of a large-scale quantum computer. So another killer application of quantum computing is to the search problem. So what's the search problem? So imagine that we have 1 million cups here turned over, and underneath one of these cups is hiding a ball. So the search problem is basically to look under these cups in order to find where the ball is. Okay? Now, a classical algorithm basically just has to go looking under probably about half of these cups in order to find out where the ball is. Now, there's a quantum algorithm called Grover's algorithm that's actually much faster at this problem. So if we have 1 million cups, then with Grover's algorithm, you actually only need to look under the cups about 1,000 times in order to find the ball. So this is what we call a square root speedup. If there's 1 million cups, you actually only need to look through about 1,000 of them. So Grover's algorithm actually gives the square root speedup. It's not as large of a speedup as Shor's algorithm, but search is, of course, a very common problem. So this can be applied in many different scenarios. Shor's algorithm is what we call a sub-exponential speedup. So this means that something like factoring a 2048-bit number is something that we think is completely intractable now on a classical computer. It would take hundreds of years. But this is something that you could do in just minutes on a sufficiently large quantum computer. Okay, so now let's see how these two killer applications affect the security of Bitcoin. Okay, so the security of Bitcoin relies on, well, there's two key factors. The first is the digital signature. So a digital signature kind of imitates what your signature does in real life. So your signature in real life kind of certifies that you authorize a certain action. And similarly in Bitcoin, when you want to send Bitcoins to someone else, you have to sign that transaction digitally. And again, this certifies that you're the one who is authorizing this transaction. And the signature has this unforgeability property. No one else can imitate your signature, therefore no one else can spend your Bitcoins. Now the security of the digital signature algorithm that's used in Bitcoin is actually based on something called the discrete logarithm problem. This is another problem that Shor's algorithm can solve. So that means that this digital signature algorithm is completely insecure in the face of a sufficiently large quantum computer that can run this Shor's algorithm. So what we did in this work from last year is we actually tried to estimate, okay, how many qubits would you really need to run Shor's algorithm in order to break the digital signature scheme used in Bitcoin. And what we found that you probably need around 500,000 to 1 million qubits in order to do this. Okay, so today we're at 50 qubits. You probably have to get to around 500,000. So that's still a 10,000-fold increase in the number of qubits you need. So we're probably looking at, assuming a doubling of the number of qubits every 8 months, this is still going to be 10 years out. But of course, this is a legitimate threat to the security of Bitcoin in the future. So another key to the security of Bitcoin is what's called the proof of work. What the proof of work does is ensures that it's costly for any one person to create two blocks too frequently in the Bitcoin protocol. So any one person can dominate the selection of transactions that are put into the Bitcoin blockchain. It's kind of a thing of 1 kilowatt, 1 vote. So basically you have to put in a lot of energy, a lot of electricity in order to be able to be selected with high probability to create new blocks in the Bitcoin protocol. Now how the proof of work works, it's actually based on a search problem. So all these Bitcoin miners are competing to solve a search problem. The one who solves it first gets to make a new block. Now you can actually do this proof of work with a quantum computer using Grover's algorithm. Grover's algorithm is exactly designed to solve these kinds of search problems. But very interestingly, what we found is that quantum computers will probably not be very competitive in doing the Bitcoin proof of work, at least not for the next, say, 20 years. And the reason for this is that specialized classical hardware is very, very fast at doing this proof of work. So devices called ASICs can do something like 14 trillion operations per second in doing the Bitcoin proof of work. On the other hand, near-term quantum computers are going to be relatively slow. In fact, even slower than your laptops. We expect them to be able to do about 100 million operations a second. So even though there's this faster algorithm that quantum computers can use, their lack of speed will totally negate the speed up from the algorithm. Okay, so we've seen two headlines from the recent news about quantum computing impacting Bitcoin. So quantum computing is not likely to rock the world of Bitcoin mining, at least not for the next 20 years. And I think it's not true that this is going to be hackable within months. We're probably looking at least 10 years for this to happen, although this will be a future threat to Bitcoin. So don't believe everything you read in the popular media, and I hope this talk will help you to be more skeptical of the articles that you read about quantum computing in the future.